Hi, my name is Dale Maley. In this short video today, I'm going to explain how or some of the engineering challenges I had in making this latest marble game. Now, a little background information, I like building the larger hand crank marble machines. I built 6 or 7 of them, and I've used 6 different ways to raise the marbles up. But then I got a new idea on another method for raising the marbles. If you've ever driven through an oil field area, you likely seen those slow moving pumping arms, and those are actually oil pumps that are raising oil out of the ground up to the surface. And here's a typical diagram for one, and they usually use an electric motor to run the mechanism, but I could always substitute a hand crank as the power source. And instead of pumping oil, I could use it to raise marbles up for a marble game. Now, I faced about 4 different engineering design challenges coming up with this marble model. The first one is the main linkage. How do you design the linkage lengths, yet they have to package inside my envelope? I like to keep them no more than 30 inches long, 12.5 inches deep or 12.25, and 25 inches high. I also want to lift the marble as high as I can, and I'll likely use 2 mechanisms to do that. Another challenge will be coming up with a piston design. The third challenge will be coming up with a loading mechanism that only loads 1 marble at a time. The fourth and last challenge will be coming up with a worm gear design. I need to find the max speed the model will operate at, and then I need to verify the fastest speed that a human can crank. And once I know that, I can calculate what gear reduction ratio I need on the worm gear. So when I first started this project, I started out designing the main 4-bar linkage. And I discovered it's hard to design a 4-bar linkage just using the SketchUp drafting program. And it turns out you have about 3 key inputs, which is the length of the crank arm, the distance on the length that's from the end of the crank arm to the rocking beam, and the length of the rocking beam. There's no way to easily visualize a relationship between the inputs and the outputs here, because you've got 3 inputs and 1 output. So you can't just use a X, Y, and Z graph to kind of give you a feel for the model. However, I did know about a free simulation program called Linkage.Exe. There's definitely a learning curve involved with using it, but it does let you quickly evaluate alternative designs. One good thing about this free simulation program called Linkage.Exe, if you try to design a linkage that will actually have interference with itself, when you try to run the simulation, the program actually stops and tells you that you have a problem, which is a good thing. So here's the process I ended up using with a Linkage.Exe simulation program. First, I developed a concept in SketchUp. And then in SketchUp, I got the XY coordinates for each of the key points in that design. I set up an Excel spreadsheet, which we'll look at in a minute. I input each of the key points into the linkage. Then I inputted each key point into the linkage program, ran the simulation. I saw and measured what the rocking beam swing angle was. I entered that into Excel, and then I kept modifying the design until I thought I had the best design I could get that would still package in my 3D limitations I noted before. Now here's a screenshot what the Linkage.Exe program screen actually looks like, with a menu on the top, and then you draw your mechanism below. It's kind of hard to see here, so we'll zoom in on just the mechanism itself. So if we zoom in on the simulation in the Linkage.Exe program, you can see on the right is the crank, rotating crank. It has a connecting link which takes it up to the rocking beam, which rotates back and forth about 45 degrees. Over on the left hand side would be where our piston is going to travel up and down in a vertical direction. Now here's a video of the main 4-bar linkage actually running in the simulation program. You can also turn on certain points and have them trace the movement, which you can see on the right. You can see the arc that the rocking beam travels through. You can also see where the crankshaft's going around the fixed point, and on the left you can see the piston moving up and down. One thing I learned about 4-bar linkages in this project, if you don't have the relationship right between the key elements, your mechanism will actually jam up. And you can calculate that and make sure that it's going to work. So I set up on that Excel spreadsheet I talked about earlier, I set up where I could calculate that critical dimension and make sure I knew whether it was going to work or not. It's very handy. Now here you can see that Excel spreadsheet that I set up for this project on the 4-bar linkage design. And the best option that I found was the crank arm would have a 2 3/4, 2.75 inch length. The connecting length would be 7 1/4 inches long, and the long rocking beam would be 18 inches total, or half of that would be 9 inches. And with this setup, it gave me about 6 inches of piston lift. Once that I just arrived at the best 3 lengths for the 3 critical elements, I modified my SketchUp drawing, and here's what the final result actually looks like in SketchUp. You can see the main center rocking arm, and then there's a right link hanging down to the crank arm, and then the left one hanging down will go to the piston. So we've now completed the design of the lower walking beam portion of the model, and then we'll duplicate that for the upper level. It has the same length of rocking beam, but I had to adjust the link lengths because that second piston is going to raise the marble up from about 6 inches up to a final height of 12 inches. The first piston took it up from 0 inches up to 6 and then dumps it off to the second piston. Now in some of my past large marble projects, the carrier for the marble, or in this case we'll call it the piston, that's been one of the toughest things to design. But this one wasn't too bad. I decided to use a linear bearing type design for the piston, where each piston is guided by 2 dowels that are 1/4 inch in diameter. I am using 1 inch diameter marbles, and then down at the bottom of the piston I'll drill an 1 1/8 hole, a little bigger than the 1 inch marble, and I'll put that at 6 degrees so gravity will cause that marble to flow to the other side of the piston. Then I'll use a vertical board to keep that marble from falling out while it's traveling up, and once it's up I'll let it drop off to a chute. So here's what the piston looks like in SketchUp connected to the rocking arm beam. You can see the red marble down there, and that's the 1 1/8 hole that's drilled at a 6-degree angle. There is a board in the back to keep the marble from falling out until it gets up to the top position where it dumps off to a chute. Okay, so at this point we have the basic 4-bar linkage with a rocking beam designed. We also have the piston designed. So next I need to figure out, when the marble returns back to the beginning, how do we load it into the lower piston? So that I'll have a chute which will load it into the lower piston, but I only want 1 marble to load per stroke. So I need an escapement. In the clockmaking business is called an escapement. I need an escapement type mechanism that only allows 1 marble to load per stroke of the piston. And how do I actuate that escapement mechanism? Well, I decided to let the bottom of the lower piston push down on a link, which in turn will raise an indexing arm up, as we'll see in a minute. So I think I fully designed this escapement mechanism just in SketchUp. It only has 3 linkage bars, so it's not near as bad as a 4-bar linkage is to design it in SketchUp. However, one could also use the Linkage.Exe program to help you design the links. And I went back and did that. So my process there was develop the design option in SketchUp, and then get the X and Y coordinates from SketchUp, because I need those to input them into the Linkage.Exe program, then run the simulation program. And I need to raise this indexing arm up a little bit above the height of the 1 inch marble in the loading mechanism. Now this is a screenshot from the SketchUp drafting program. with the key elements shown here, and I use SketchUp then to measure and determine the XY coordinates because I need to input those into the simulation program. Now here's what the escapement mechanism or loading mechanism looks like after I input it into the Linkage.Exe program. Now in a second we'll run the program and you can see what happens. Now the bottom left hand side will be where the lower piston comes down and pushes down on the linkage mechanism, which in turn then raises the little piece that holds the marble in place, as we'll see in a second. So I'm using a linear actuator to simulate the piston moving up and down on the bottom left hand corner. Now here's what the final design actually looked like in the SketchUp drafting program. You can see my orange arm that will move up and down. The blue piston, when it moves down, it hits that red little beam below it, which pushes up on the light blue link, which raises the orange arm up and lets one marble go in. And when the piston goes up, then it causes that orange arm to fall down and hold the next marble and keep it from loading. Now here's a video of the finished model, and you see the blue piston moves down, hits the red bar down below. Here it comes. It's going to hit the red bar, which is going to raise the blue bar up and the orange one up, and when the orange linkage goes up, it allows one marble to load. Now you see it go back down and it keeps the rest of the marbles in place. Now we will zoom in just a little bit closer. Maybe you can see the mechanism a little bit better. So my last design challenge was to come up for the worm gear design. So I built just the key parts of the model so I could find out how fast can I run it before bad things start to happen. And it seemed like 12 RPM, the model really wanted to run pretty well at that speed. Then I redid some tests. I wanted to verify the fastest that a human being can crank one of my models, and I ended up using a video to record myself cranking as fast as I could go, then playing it back in slow motion where I could count the number of revs and the time period involved. I was a little bit surprised. I could actually crank at about 202 RPM. So the gear reduction ratio I need is the 202 max divided by the 12 the model will run at, which is 16.8. So I rounded it off and I chose 16:1 reduction ratio, which means I'll have 16 teeth on the gear that mates with the worm gear. So here's what the 16:1 reduction ratio worm gear setup looks like. And you can see my other videos on how to design and build these wooden worm gears, and also the mating spur gear, which in this case I actually have angled teeth on it to match the angle of the worm gear. Now let's take a look at the model in action, which will finish up this video. So, some closing thoughts on this project. If you like some engineering design challenges, this is a very fun project. I also learned the simulation program Linkage.Exe. It can really be a valuable design aid, especially when you have 4-bar linkages involved. So in summary, This video explains the design methodology that I used to design this new marble machine. Please see my other videos with my many other marble machines. Hopefully this video helps you on your projects. I hope you enjoyed the video, and please subscribe. Thank you.